we're looking at those types of things, right? When you're going sledding, when you're going down a slide in elementary school, things like that. And so we obviously have friction involved, but sometimes we'll neglect friction or negate friction in our problem solving, depending on what the problem is, right? The one thing you got to remember is normal forces are always perpendicular to the inclined plane or the surface, right? So obviously we've been looking at this type of situation on the left, but when it becomes inclined, right, just you tilt your head, the normal force is now still perpendicular to the surface, right? It doesn't go up like this. It's always perpendicular to the point of contact. That would seem to be one of the issues some people had with just force diagrams when we were doing that a couple weeks ago. And then the driving force, right, when we look at this, the force of gravity still acts straight down. What we're doing, though, is we're going to make this the x-axis, the incline, and therefore the y is obviously perpendicular to the x. That makes the force of gravity, right, straight down, but not in the y direction anymore. And we talked about this a couple of weeks ago or a week ago as well. The reason why we do that is we want to resolve the least amount of forces into the components as possible. And so by rotating the x-axis to be along the incline, that means the force of gravity should be the only force that we have to break into the x and y components. And so what we do is we get rid of the force of gravity and we break it into the x component, or a lot of textbooks like to call it the parallel component to the incline, and then the perpendicular component, which is really the y equation, right? And see if I can write correctly here, right? And basically instead of drawing it down here, what they do is they take it and they move it up to here, right? Which is, it's this and this is still the same, but what you'll see on one of the slides, or if you looked at the pre-lesson, right? Whatever this angle theta is here, this angle theta is also, right? And you can see that if you kind of you make this, if this is 30, this is 90, this has to be 60, right? Here's a right angle also. So if that's 60, that has to be 30. It will always work out that whatever this angle of the incline is, the angle inside my triangle for the force of gravity for the components is going to be the same. But, right, if this is the force of gravity down and this is the parallel component, or FGX, right, it's opposite the angle. Opposite is sine, right? And we're used to the x component always being cosine. This is the exception to the rule based on this geometry. And then I wish that they drew it up here, but the parallel or the perpendicular component is really the y component, is adjacent to the angle. And so when we find FGY, or the perpendicular component, we're actually using cosine. So inclined planes, that whole idea of x always having cosine, right, goes out the window there. This is kind of the exception to how that works out. But we replace this force of gravity with the two components, right, when we solve these problems. And then this just kind of shows you that, which hopefully makes sense, as your angle increases, the parallel component will increase and the perpendicular component will decrease, because eventually if this was 90, then it just falls straight down and then there wouldn't be any perpendicular component because it would free fall. Right, and these are all slides I had in the pre-lesson. So again, I'm not going to spend a lot of time on these. Right, there's our force diagram without friction, and then we obviously would have friction. You have to figure out which way you want to make positive though for the x. And it's if you know that it's going to slide down the incline, you can make down the incline, right, in this case to the left positive. Obviously this could be rotated 90 or 180 degrees and face the other way, and then it takes care of itself, because down the incline would be to the right. Generally though, textbooks will make motion down the incline positive, no matter how it's drawn. But that, again, that's up to you. You can make this positive and this negative. Again, we've talked about that from day one. You get to set the stage for how you want to solve your problem, right? But we do want to choose the x and y so that it looks like this, right? Again, and so if you think about, you're looking at that head on, but if you tilt your head the same amount that the angle is, well, then it's normal, right? Now you're looking at x and y, and so that's kind of the silly little thing that I always say is it's tilt the head method. This just shows you why the angle inside is theta, and it's always going to be that. So whatever this angle is here, this angle inside of here will always have the same value. And this shows you the geometry. Again, if this is 30, then this has got to be 60. So then this has got to be 30 because this is also a right angle. Right, and then we're going to end up by replacing the X and Y components with their value. But I'm going to show you that when I do the math. Didn't realize I had so many little things to click through. Right, and this is the way it works out, that the perpendicular component, again, we use cosine, which is really the y component, right? FGY, FGX. So what happens is, right, the perpendicular component is if you're going skiing this weekend, let's say we're getting snow, maybe you're going to go skiing. The perpendicular component is what keeps you touching the slopes. What is the accelerating force is the parallel component, right? And so obviously, if you go to a green, I forget what they are, green squares, blue circles, or vice versa, and then you get to the black diamond, right? That makes the angle bigger and bigger and bigger. And so as you go to a steeper slope, then this force gets bigger, and that's why you go faster, right? The driving force to go down on your skis is the parallel component. It's the engine. The perpendicular component keeps you in contact with the slope, which is pretty important usually. And this shows you applying the X and Y kind of like in a basic situation without friction. But I want to do that and kind of walk you through it. Again, this was all in the pre-lesson. And so this I liked because, and I didn't make this up, somebody made it up and they rotated it. And so now if you look at it like this is kind of what we're doing. If you want to relate it back to just the normal, take away the fact that it's an inclined plane. And if you think of it like this, normal force is up, right? Your driving force is to the left. And then you have just this force here. Well, this is the force at the angle you're breaking into the X and Y component. And so there's a way to make it look like everything we've been doing if you rotate the incline and look at the force of gravity just acting down into the left or right, depending on how it's drawn. Right, and this just shows you how we make the triangle. I kind of skipped through that a little faster, right? And how we find the X and Y component based on trig. I wish I hadn't made so many things stepping in. Lots of thetas. Right, rotate the axis, break weight into its components, write equations of motion, and then solve. So this is what I wanted to get to, with and without friction. We don't have a lot of time. All right, so there's some really nifty results. They're derived equations, okay? So we'll start out with no friction. And so if there is no friction, right, I want to make my force diagram. So I'm going to call that the normal force. Didn't mean to draw it there, but I'm not drawing very straight lines. There's the force of gravity. I'm going to use, so that way I'm not having so many subscripts. I'm going to use those symbols. Okay, and so we're ignoring friction. Now, obviously, if there's no friction, doesn't matter what we have on this incline, it's going to slide down the incline, right? And so we know it's going to move in this direction. Doesn't matter what it is. With friction, depending on how heavy it is, right? And so how much, because remember the driving force, what's going to make this slide down the incline is the parallel component of the weight. And so with friction, right, the friction could be great enough to keep it at rest, and it obviously would be up the incline. So again, you have to decide what's positive and what's negative. I'm going to make down the incline. I wish I had flipped this around, but I don't know why I didn't. But I'm going to make down the incline positive, so I'm working with positives. So I set up sum of the forces in the x equaling ma, sum of the forces in the y equaling 0, right? So this is in the y. This is my, I'll draw it over here, but this is going to be positive x, my negative x. Okay, and again, it doesn't matter how you want to do it. It's just like when we were doing free fall. If you want to make down positive, you can. It's up to you. So when we look at this and we don't have friction and we're not pulling on this up the incline, or there's no other forces. We're looking at the most basic inclined plane problem. What we have to do then is we have to break. We have to break the weight into its perpendicular and its parallel component, right? As those other slides showed you. And then whatever this angle is, right? Because this is a right angle and this angle is going to be the same angle theta. So now we want to make our equations, right? And so, I should have. Since I used F perpendicular and parallel there, I guess I should be somewhat consistent. That would help. So I will call that FG. And this would be FG Y, or you can just put F perpendicular, or FG X. So now I want to make my equations. In the X plane, I just have this component, right? That's the driving force. This is what makes people go down the ski slope, or if you're going sledding, right? That is the driving force. So I'm going to put F parallel equals MA. Over here, I have the normal force up minus, right, the perpendicular component equals 0. Now, when we look at this, right, basically what I'm going to show you is how we solve for A for this, because it's our simplest situation. We have to have those forces. You can never not have force of gravity in the normal force. But we could obviously add tension and friction and other forces. So again, we want to look at this and say, okay, well, opposite my angle I know is sine, right? Sine of theta is opposite over hypotenuse. This is my hypotenuse right here, right? It's just my triangle, instead of being like this, the way we'd like to have it, is rotated. And so the parallel component is FG sine of theta, right? Which this is the X component. Whether what you either call it this or you call it this, one or the other, whichever you like. So I'm going to substitute in over here FG sine of theta equals MA. Now over here, adjacent to my angle, I have, which is cosine, I have the perpendicular component, right? They've switched places in terms of our triangle, the way we've made them before. So the perpendicular component, or the y component of gravity, is equal to FG cosine of theta, right? That's really the only difference with an inclined plane, because then when I come over here, I have the normal force up minus the perpendicular component, which is FG cosine of theta equals 0. And what you're going to see is for the y, generally, very few problems I can think of where that's not going to equal 0, but this one is always going to be the one that's equaling MA. So, well, we can't calculate the force of gravity, but how do we calculate the force of gravity? Well, it's mg. Right, and now when I look at over here, I've got the normal force minus mg cosine of theta equals 0. Now, because there's no friction, I don't need to know what the normal force is unless the problem asks for the normal force. So that's what really the only reason why I'm showing you this part is how we set it up, because there's going to be problems where they say calculate the normal force. And when there is friction, we need to calculate the normal force. But if they make it a frictionless problem, Well, you can look and say over here, well, I can solve for the acceleration. I don't need to know what the normal force is, right? But the normal force, instead of equaling mg as it has been for the last week or two, now it equals mg times the cosine of theta. And this is the result that we get on an inclined plane, right? And so if you know cosine of 0 is 1, right? So what does that mean? That means it's a flat incline, right? It's the floor that your feet are sitting on. And so the normal force is equal to mg. If we put in the cosine of 90 is 0, right? That means it's straight up and down. Well, there is no normal force because it's falling, right? And so that's how it goes from the maximum value of mg, but as the angle increases, it goes to 0. Now over here, I look at this, and again, this is where, right, the problem may not give you the mass, and it can't be that you're like, oh, I can't solve this problem, because you see, when you work it out with letters, this is why they don't give you the mass. And so the acceleration is equal to g times sine of theta, right? And so this is a nifty little result to calculate the acceleration. What is the acceleration of any object on an incline with no friction? Now, I show you this, but you can't just memorize this and say, oh, I saw Doc derive this, I'm going to use it all the time. You wouldn't get any credit for that, right? You have to derive these things to get the credit to do that. It's neat that it does that, and it does that for a lot of different aspects of Newton's second and third law. But essentially, you'll see what determines the acceleration of something going down a frictionless incline. Well, it's gravity, and it's the angle of inclination, right? And as you go to 90, right, sine of 90 is 1, a is equal to g. It's free falling, right? If theta is 0, then you have sine of 0 is 0. There's no acceleration, right? All the things sitting on your table are not moving because there's no acceleration. It's a flat surface. So this is the result we get, and it's a pretty straightforward result for no friction. Any questions on that? Again, the one bad thing about using annotate with Zoom is that once I want to go to a new slide, I have to erase everything because it stays, and we're not going to want that. Okay. So obviously with no friction, it's a lot easier. With friction, it's obviously a little trickier. I can't make the slide go. So with friction, did it do it? Did I click on that twice? No friction. Okay. All right, same thing. But now what happens when we add friction? Right, the normal force. This is going to be y. It's going to slide down the incline as long as, right? And so that would mean friction is up the incline. I won't draw it right there because otherwise you wouldn't see it. And then I'm just drawing this bigger so that way I don't want to use that. All right, FG. So again, it's going to accelerate down the incline if it moves, right? And so we can look at two things here. First, we'll look at what if it doesn't accelerate? What if it doesn't move? We put it on the incline and it sits right there. That means, right, when I break the force of gravity into its two components, right, the FG y direction, or F perpendicular, and then again, you get to choose the symbols that you want to use, FGX or F parallel, right? And this angle, whatever this angle is, if this is 20, this is 20, it's going to be the same. So let's look at first, what is friction, no motion. Acceleration is equal to 0. So then if the acceleration is equal to 0 for the first part, right? So we need to overcome static friction to make this thing move, right? And so that would mean this force has to be greater than the force of static friction to make it move. All right, so now we set up our equation. It's not moving, so x equals 0. Y is always going to equal 0. Now, when I make my two equations, draw a very good end there, right? The normal force minus Fg, the perpendicular component, equals 0. In the y direction, right, I now have Fg parallel minus the force of static friction equals 0. Right, so the only thing different from this problem and the last problem is I've added friction. Setup is the same. All right, so now we got to simplify this up. Normal force is going to be equal to, or normal force minus this, right? It's adjacent, so we know it's cosine. I kind of showed you that already. So it's Fg cosine of theta, and that is mg cosine of theta. And again, you're going to see for an inclined plane with friction, without friction, that this is what the normal force will equal pretty much every time until we start adding, and there's, I think in the example, the pre-lesson, I had an AP question I put in there that I had worked out where they were pushing here. And that made it so you had two forces you had to break into the X and Y component. Obviously, that's a little bit harder than this problem, and that would change what the normal force equals. For the basic inclined plane problem, you're going to get this result every time when you do the Y forces. Now, the difference is over here, right? It's not moving because this, right, has to be greater than the force of static friction, right? We talked about static friction being the greatest amount of force for most 99% of the situations. And so this is going to be Fg times sine of theta, right, minus force of static friction equals 0. How do we calculate force of gravity? We know it's mg. Force of static friction, coefficient times the normal force equals 0. So this is why we need it now, because right here's the normal force, and this is what the normal force equals. Okay, so now when I come over here, I'm going to do some substitution. Right, so that I don't have. This is broken down into the simplest things we can. We can't break any of this down any farther. Carry through the coefficient of static friction, but now we're going to substitute in this result, right? Mg cosine of theta equals 0. Now, when I look at this, there's a couple things that are common in both terms, right? I have two terms. I have mg and I have mg. So you can factor, but for some reason, factoring seems to be something people don't see right away. So what if I get these things on the opposite side? Right, usually when I do that, then people are like, oh, I can factor out the mass. I can factor out g. Now what am I left with? Sine of theta equals coefficient of static friction times cosine of theta. Well, what if I divide both sides by cosine of theta? What is sine of theta over cosine of theta? Hopefully you guys know that one. It is tangent of theta. Right, and so we get this nifty little result that if we wanted to know if we know the coefficient of static friction between whatever this red square is and the incline, we can find the angle at which this would start to slide by simply taking the inverse, right? Because usually this is less than 1. Although I'm not great at, I know sine, cosine, but tangent, I think you can do greater than 1. But we would do the inverse, and that would tell us the angle of inclination that would make this block start to slide, because at that point, this force would be greater than this force. So it's a cool little result that you get. Obviously, it's a shortcut to some problem solving. but you would really need, and so it's been something that you've had to derive before. And so you can see there's a lot of, I've not skipped any steps, so it makes it look a lot longer. As you do these, hopefully you'll start to skip a couple steps, and not, write everything out in such verbose detail. But that's one of the nifty results with inclined planes. Now the other one is to find the acceleration. Okay, and so I can stay right here, I guess. I don't need to go anywhere. So let me do this again. There's the normal force. There's friction. And so what I'm showing you are kind of the most common, like if you open up a textbook, you're going to see these different things derived. Right, there's my force diagram. We have friction, but now we want, it's moving, so it's accelerating. Right, and so it's going to accelerate down the incline. This is the force I have to break into its components. Right, and that angle is always going to be theta. So this is the perpendicular component, the parallel component, right, the y component, the x component. So when I set up my two equations, now they're going to equal ma, right? So we're applying a force. What that means is this has got to be greater than this in order for it to accelerate down the incline. There's my two equations. Now this doesn't equal 0, it equals ma. Again, this is going to be just what I wrote a minute ago. Right, the normal force minus the perpendicular component of gravity, or the y component, right, is equal to 0. The normal force will equal that. How do we calculate the perpendicular component? Well, how do we calculate the force of gravity? We know it's mg, and it's cosine of theta, right? And so we get this result. And so when we set n equal to mg, as we have been, it's really just n equals mg is a special case when the angle is 0, right? Now over here, this is where it gets a little tricky. So let me do it in a different color. I'll do it blue. So again, we have the driving force, the force of gravity parallel to the incline, or the x component, minus the force of friction, but now it's kinetic friction equaling ma. And what we want to do is I want to solve for the acceleration to show you the result and to see how the acceleration value changes when you have friction. All right, so we need to substitute in here. Well, what is this equal to? It's always opposite. So how do we calculate the force of gravity? It's mg, but it's opposite, so that's where we use sine, right? This is mg times sine of theta, as I showed you in the very first derivation. How do we calculate the force of kinetic friction? It is the coefficient of kinetic friction times the normal force, equaling ma. Now again, I can't break this part down. Mg sine of theta is broken down to its basic parts. Coefficient of kinetic friction is a value. But again, this is where we substitute in what the normal force is equal to, mg cosine of theta, and that all equals ma. Now, when I look at this, right, I have m, and m. And so this is again why in a lot of those problems, mass is not given, because it doesn't matter what the mass is. And so if I rewrite this, g sine of theta minus coefficient of kinetic friction, g cosine of theta equals a. Now at this point, you can factor out the g if you wanted to, or you don't have to. And so if you look at this result for acceleration, and you look at the result that I had when there was no friction, right, we got this. Well, think about it. If this is the greatest amount of acceleration we can have on an incline, if we add friction, it's gonna make it slower, right? A lower rate of acceleration, and so we're subtracting this much from this. And so if it's frictionless, then this all becomes 0, and now we're back to this. So again, this becomes the simplified case of this, because when there's no friction, this is 0. 0 times all of that makes it go away, and then we end up with this result. And so this is how we calculate acceleration when there is friction. So, and the reason why I'm showing you this is because we get these, right? It's all letters. This is college physics. This is what college physics looks like every single day. And you would probably walk out of the class not solving one problem with numbers, right? That is engineering every single day, right? And it's for whatever reason, it seems to be very uncomfortable for students in high school to not get an answer and just get these results. There's a couple other nifty little results that I could show you, but I'm not going to based on time because I want to at least do one problem with you. So we're looking at this. Now notice the first thing in this problem is it gives you the weight and not the mass, right? Which is easy to overlook right here. And so the weight is equal to 10 newtons, right? But the mass is not. So if the weight's 10 newtons, you got to remember to set that equal to mg. And so m is equal to w over g, which obviously would give us 1 kilogram, right? 10 over 10. So a box of weight 10 newtons rests on an inclined plane. The plane is tilted, and when the angle reaches 40 degrees, the box is just about to slip. Show that the coefficient between the box and the plane is 0.84. So that means it's not moving yet, right? And so what would I do for this? Well, I would say sum of the forces in the x equal 0, right? So normal force, friction, right, and the force of gravity, right, are 3 forces. Now for part A, it's not moving. So we know that we're dealing with static friction. And so it's asking us to prove that the coefficient of static friction is 0.8. So that result that I showed you, right, tangent of 40 should give us 0.84. That's what I'm going to basically be proving. Now, because this has 2 different parts, but the inclined plane stuff in the y direction is not going to change. You don't need to rewrite it over and over again, right? And so you look at this, we know, so this is a y direction, down the incline, right? This is a better way to have the incline because now we're looking to the right as x. But we still have to break the force of gravity into its 2 components. And I'm only doing it up here on this picture because I don't have a lot of space on this slide, right? That's the perpendicular. Here's the angle. This is 40 also. And this is the parallel. Same as what I did on the other 3 things that I showed you. So when I set up my 2 equations, the y equation for part A and part B is not going to change, right? It's going to be the normal force minus Fg perpendicular equals 0. The normal force minus mg, right, which we know is 10 newtons, times cosine of the angle, which is 40 degrees, equals 0. Right? So, well, let me not put in the angle yet, so that way at some point I can kind of, right? Let's close that. Right, I'll just call that theta for right now. So n is equal to mg cosine of theta. That result's not going to change, but in part B here, we notice that we change the angle to 50 to make it start sliding. So over here, I would say, right, what's going to make it, or what's trying to make it slide down the incline? Well, it's the force of gravity that is parallel to the incline, right? This is the force that's trying to make it go down the incline. And static friction is opposing it and not letting it do that. So now, what do I plug in for this, right? Well, we know it's mg sine of theta. In this case, it's 40 degrees. How do we calculate static friction? Coefficient times the normal force equals 0. Now, for part A, so let's do this, because this is probably what a lot of you guys would do, is you'd say, all right, well, I know the angle, I know the mass. Let's get a number here, right? So this part right here, remember, m times g is 10 newtons times the cosine of 40, right? So what is the cosine of 40? 0.766. So if I multiply that by 10, I obviously get 7.66. So you can round that up to 7.7. When I come over here, right, we're trying to prove that this is equal to 0.84. Now, let me take this one step farther. Right, this we know is 7.66. If we didn't, right, we could substitute this in here. And again, we're trying to prove this is 0.84. The mg's cancel. Right, and then if I get this on the other side, I end up with this result. So you can derive that, not have to calculate the normal force, plug in tangent of 40, and it better equal 0.84, otherwise we got a problem, 0.839. No units, right? Now, some of you might not have done that. So let me go back and say, all right, what would you guys have done? Right, you might not have canceled out the mg. So let me do what you guys might have done here. Right, and so if I get this mg sine of theta equals, I get them on opposite sides, cosine of theta. So you know, again, this is equal to 10, right? Because it's the weight, mg is the weight, 10 newtons. Sine of 40. Right now, we already know this is 7.66, so I'm going to bring that over here, 7.66. So if I do 10 times sine of 40, right, multiply that by 10, I get 6.4. 6.42 divided by 7.66, and I get 0.839. Right, and so that's if you're not going to work it out with letters because you're given the mass, which some of you guys. Yeah, it's fine if you round, of course. Nice. All right. All right, real quick, I'm going to go through part B. Again, and so what I did before is part B. The box is now held on the plane. The angle increases to 50, so now it's going to accelerate. They tell you the coefficient is 0.5, calculate the acceleration, right? And so this part is not going to change except for the fact that now we're using 50. So you don't need to rewrite it again, right? If there's a part A and a part B, that would be crazy for you to spend your time to rewrite it again. And so just write the x equation, because that's the part that's kind of changing, right? We have Fg parallel minus the force of kinetic friction equals ma. We're trying to solve for a. So what if I kind of do this? Fg parallel minus F of friction kinetic, and I'm dividing by m. All right, well, how do we calculate Fg parallel? We know it's mg times sine of theta. How do we calculate friction? It is the coefficient of kinetic friction times the normal force, all divided by m. So mg, so we know that's 10 newtons. Sine of 50 now, right? For part B, it's at 50. Minus 0.5, because they give us the coefficient of kinetic friction is 0.5, times the normal force, which, right, is going to be different for part B, because it's going to be 10 newtons times the cosine of 50 degrees, right? So cosine of 50 times 10, 6.427, 6.4. So that would go in right here, right, for the normal force. And then I'm dividing it by the mass, but we know that if the weight's 10 newtons and we set that equal to mg, the mass is 1 kilogram. Right, and as I showed you before, the mass would have canceled out anyway, but since you have numbers, I'm pretty sure you guys would work it out like this. 10 times sine of 50 is 7.6 minus 3.2. Divide that by 1, right, which gives me, what, 4.46? So we'll just call it 4.5 meters per second squared. Now, once we've done that, calculate the final velocity of the block if it's 4 meters above the ground. So we want to know how fast would the block be when it reaches here, right? But we wouldn't use 4 meters because this is 4 meters. We would need to know this distance. And so then, so I'm not going to work this all out for you because I think you guys can handle this. But we would use this equation. We know this is equal to 0. It's not moving. Then it starts moving, right? So V is going to equal square root of 2a delta x. A is 4.5. We just calculated it. But to get x, knowing this is 50, this is 4 meters, we need to know what is x, right? Opposite over hypotenuse. 4 meters over x. X equals 4 meters over sine of 50, right? That value is what we would put in right here. This was a IB question years ago, where the students had to walk through all that to get the velocity. I'll work it out real quick. 4 divided by sine of 50 is 5.2. What did I do? Let's try that again. 5.2 times 4.5 times 2 square root 6.9, 6.85. Is what I got.